everyone, this is Athota Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering, and I'm dealing with the course Computational Aerodynamics. So in today's topic, we will see the problem solving and case studies on Module 1. So in the previous sessions, we have completed the definition terminology. So in today's session, we will see the problem solving and the case studies on the Module 1. So in this, the first one is all about how the continuity equation is derived from the models of fluid flow element, and how can we convert conservative to non-conservative form. So first here we should know basically what is conservative form and what is non-conservative form. Okay, so how do we model fluid flow? So we take an approach called control volume CV. So control volume can be an imaginary volume, so which is actually stationary or moving with respect to flow. So basically this velocity of CV will be 0 or velocity of CV is non-zero. So these are the two cases which are possible. One, velocity of CV is equal to 0, other one, velocity of CV is not equal to 0. So velocity of CV equal to 0 in the sense what? This control volume is not moving. So the fluid flow which is entering, so it will leave through the control volume, through the control surface. So it will come in, it will go out. Okay, you have in, you have out. So flow in, flow out. So whatever the flow that is entering, okay, and whatever the flow that is leaving, and what is the change that is happening, mass flow rate that is happening inside the control volume, we need to know. So basically control volume is an imaginary volume. There is nothing like in general there is no control volume, but we just draw an imaginary volume, so where we will actually see how the fluid behavior is changing when it is entering, and inside the control volume whether the fluid behavior is changing or not we will see, and then when it is leaving the fluid behavior is changing or not we will see. So example is like, you can take it as like you have engine. So here let's say you have this, yes. So let's say you have inlet for the engine. So let's say you have compressor here. Okay, let's say you have combustion, and let's say you have outlet. So when flow is coming inside, so what happens? Whatever the flow energy which is present in the ambient place is different. When it is taken inside to the ambient, or let's say when it is coming inside, so it is different actually. So when it is coming inside in the sense what? So there is a change in pressure, or either there is change in velocity. Basically the velocity is reduced. So for the engine what we do is like at the inlet, let's say you take gas turbine engine, so turbojet, turbofan, turboprop you take. So you take that as a engine as a control volume, where at the inlet, so the velocity is reduced. So when the velocity is reduced, according to Bernoulli, what happens? There is a rise in pressure. So when there is a rise in pressure, so what happens actually? So here, in turn, there is rise in temperature also. Okay. So why we do decelerate is, so the velocity, the flow when it is reduced, so we will guide that flow to the compressor to still rise in actually pressure. So the purpose, so there are different stages of the compressor. So starting from the low stage compressor to high stage compressing. So when it is undergoing the compression, so what is happening is that the flow pressure is increasing compared to the atmosphere. And when we increase, automatically temperature will increase. So here what is happening? At the inlet, the flow behavior is changing, and when it is passed to the compressor, the flow behavior is changing, and from the compressor you will send to combustion chamber. So when you send that flow to combustion chamber, the flow behavior will change, and what happens? It will ignite actually. So you will add fuel. Let's say you will spray some amount of fuel to the compressed air, and you will just ignite. so it will burn. So then it will go to the turbine outlet. So from the turbine outlet, so you do some work, what is it, the flow will leave actually. So at each and every state, the thermodynamic variables, basically pressure, temperature, velocity, density, so these values are changing at different stations. So if you consider this total, let's say this engine as control volume, so where this is actually what is it, covered by the boundaries. So basically you can see this is a boundary. So where you have velocity in, flow out. So here when the flow is getting in, there is a thermodynamic change. When it is getting compressed, there is a thermodynamic change. When it is entering the combustion chamber, there is a thermodynamic change. When it is going to the combustion and turbine, there is a thermodynamic change. Okay, so these things are happening actually. So control volume is a concept where you can assume any geometry. It can be open, it can be closed, isolated. So there is nothing, there is no rule that you have to take this or that. Okay, so it can be a open system. So basically, it is an open system where you have in and out. So you have closed system where the boundaries are closed. So isolated system where you don't have even mass or you have energy in or out. So these are the cases what we have. So now coming to our question, so where conservative form in the sense, so whatever the control volume we have when it is stationary, and when we derive these governing equations for the stationary control volume, then we say the equations what we derive is conservative form. So this is for conservative form, and when you have not equal to 0, so let's say the control volume is moving. Example is, let's say, aircraft engine. So when the aircraft is moving, ultimately engine also will move. So the aircraft engine moves with certain velocity, and the ambient air also will move with certain velocity. So it will intake that ambient air, and what happens, there is a relative change in velocity, there is a change in temperature also. So these things will happen actually. So the relative velocity between the flow and the engine has to be taken. So when the control volume is moving, and same we derive the conservation of mass, we derive conservation of momentum, conservation of energy. So you take any control volume. So when you see, or when you want to evaluate the flow physics, flow entering, flow accumulating inside, and flow leaving through the control volume to the control surface. So with these aspects, so we derive energy equation, momentum equation, and continuity equation. Okay, so when it is fixed in space, we say the equation what we derive is conservative form. So when it is moving with the space, we say that the equations are non-conservative form. So that is the difference. So coming to question, so what continuity equation? So basically, simple continuity equation is in general, m dot is equal to constant. So what is m dot? Basically, what is mass? Mass is equal to density into volume. Okay. So mass m dot is constant in the sense what? You take any section here. So you take here, 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 here. Any section 1, 2, 3, 4. At the sections 1, 2, 3, 4. So your mass, the rate of flow rate, or let's say mass flow rate here, here, here will be constant actually. Okay, so whatever that is going inside, that has to come out. So that is the basic entity of the continuity. Okay, now what is happening actually? So when m dot, so basically m dot is nothing but rho a v. So why we are taking a into v? Why? Because so here mass is equal to density into area into length. So when you differentiate this with respect to, let's say, time, so this will become m dot. So when you differentiate this one with respect to time, so what happens? This term will be replaced as velocity. So therefore, this will be rho av. Okay, so that's why you have rho av. Now, so let's say you have some this thing. Sorry. So you have this section 1, 2, 3. So let's say you have some m dot. So m dot at 1 should be equal to m dot at 2 should be equal to m dot at 3. So the meaning is, so mass flow rate at section 1, section 2, section 3, all these three places they are equal actually. So since it is the mass flow rate is constant, so it is constant. Now where the changes will happen? So we have three parameters: rho, which is density; A, which is the cross section area; next velocity. So if you take the flow as incompressible, so this parameter will not vary. The density will not vary. So area and velocity will vary. So here what is happening, when there is a decrease in area, there will be increase in velocity. Why? Because if area decreases, the velocity has to be increased such that AV is equal to constant. Okay, so this is under incompressible flow assumption. So when the flow is getting compressed, so even density also will change. Okay, so density at each and every section will change. Now in the first section, what is happening? It is converging. So area decreases, then velocity should increase at this section. So at second section, here and here, the velocity is like, let's say it will not vary. Let's say it's constant. Why? Because the area is constant. When it is entering the third section, area is increasing, therefore velocity will decrease. Okay, then what happens actually in the first section when it is going to the convergent? So the pressure will decrease. So P is constant here, and pressure will increase. Okay, so this is constant, this will decrease, and this will increase. Okay, so this is what happens for this section. So what is happening when the density, when we take the flow as incompressible, so when we take this convergent and constant and divergent section, so first what happens, the pressure, or let's say what we take the pressure decreases. Why? Because area decreases, velocity increases. In the second section, what happens? It is constant. Why? Because there is no change in area. Third section, what happens? So there is an increase in area, therefore increase in pressure and decrease in velocity. So this is what happens. So this is small background about m dot is equal to constant. Okay, so this is what happens. Now let us see in integral form. Okay, so we'll see in integral form, and so then we will change into differential form. Okay, so we take this. See how inside we take some small element, so which is ds. So we take this control volume, which is of dv. So we have flow coming inside, we have flow going out. So v dot n. So it's a surface actually. If both are in the same sign, so let's say this is on the same sign, the normal vector. So this is the area normal vector. So this is negative for the inflow. So v dot n will be positive for the outflow. Okay, so this is what we have. Now what is happening? So the rate of decrease of mass inside the control volume. So basically when we say rate, dou by dou t. The rate of decrease of mass. When I say decrease, you have to put negative. Okay, and decrease of mass, rho into v. Okay, so the rate of decrease of mass, so inside the control volume, so we have to apply the volume integral, is equal to the flow which is leaving through the control surface. So here you have some x amount of mass inside the control volume. So when there is a decrease of mass delta x, x minus delta x, what happens? This delta x amount is going outside. So that's why there is a decrease of mass inside the control volume. Okay. So therefore, what is happening actually? This x minus delta x, what is that? Is the rate of decrease. So of mass, which is equal to the flow which is leaving out to the control surface. So here you see the control surface. So surface. So actually here into dv. So rho v dot dn. So this is what we have. Okay, ds surface. Okay, so this is what we have actually. Fine. So when by applying Gauss theorem, what is happening is like, so the surface integral can be changed to volume integral. So where this term is changed to del dot rho v velocity into dv. So by Gauss theorem, the surface integral is changed to volume integral. Okay. So finally, what is happening? So this minus dou by dou t of volume integral, let's say you can take this. So of rho into v dv is equal to, so the volume integral of del dot rho v dv. So this is the final expression here. Okay. So at the end, what happens actually? So when you rearrange the equation, so simply we have the common term volume integral. You can take it. Dou by dou t of rho. Sorry, this become into dv. This is the volume of the to dv plus del dot rho v to dv equal to 0. So this is what we have. So this is the final form of the continuity equation in integral form. Okay. So when you change this one, when you take that integral term common, the dv get cancelled, then it is changed to differential form. Okay. So finally, so if we see the equation changes, dou rho by dou t plus del dot rho v equal to 0. So this is the final form of continuity equation. So when you want to take non-conservative form, what happens? This v, so v will be equal to v minus v of cv. The relative velocity will change. Okay. So dou rho by dou t plus del dot rho v minus vc equal to 0. So this is what we have in non-conservative form. So basically the relative velocity between the fluid will change. So and the whatever the amount of the flow that is entering or amount of the flow that is leaving, so that will be constant. But so here in addition you have the relative velocity. So this is what we have for the difference between conservative and non-conservative form of continuity equation. So we have taken the model of control volume, which is rest, and then we have extended it to control volume which is moving. So with this we have seen the problem solving technique or the case study for the module 1. So in the next session we will see the other cases. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.